Let's talk about partial fraction decomposition. We have for many years been able to add fractions with no problem. We know that process. We find a common denominator, we use a well-chosen one, we combine them, and we have one fraction. So we can take two fractions and add them, and the result is one fraction with a common denominator. Here, there are several types of partial fraction decomposition. We're going to talk about only linear factors in our denominators. So as I said, we're very comfortable combining fractions, even fractions that have linear factors as denominators. We know we can find a common denominator by looking at the denominator, seeing what factor is missing, and multiplying both top and bottom by that missing factor. And that will give us, for both of these terms that we're adding together, it will give us a common denominator. We multiply through on the numerators, we collect the like terms, and we clean up the numerator. So we know that 3 over x plus 2 plus 5 over x minus 1 is equivalent to the fraction of 8x plus 7 over the product of those two denominators. But what about starting with this fraction and decomposing it to find the original two terms that were added together? And that requires decomposition. That's why this is called partial fraction decomposition. So we would work this backwards. Let's say we didn't know what the original numerators were. We just know what the final product was of adding those two terms, those two fractions together. So as we saw in the previous slide, the denominator factors to x plus 2 times x minus 1. So we have two linear factors in our denominator, and we know that we had numerical numerators, but we don't know what they were. A and B is what we're going to write. And we do use capital A and capital B. That's the notation that is used by all mathematicians. But the bad news is we can't just look back at the previous slide. We've actually got to figure out what A and B were. So here's what that process looks like. We are going to multiply both sides by the denominator so that we just get one equation with no fractions. So I have an equation here. I'm going to take this denominator in its factored form and multiply by the numerator so that all I'm left with, because this cancels with this, all I'm left with on the left-hand side is 8x plus 7. When I multiply on the right-hand side, I'm going to wind up with a times x minus 1 plus b times x plus 2, because x plus 2 will cancel in this first term and x minus 1 will cancel in this second term. So now I have an equation, and I can distribute a through those parentheses, distribute b through those parentheses, and I know when I gather like terms, I have a plus b times x if I factor the coefficients out, and I have negative a plus 2b, and so this has to be the coefficient of x, which is 8, and this has to be the constant value, which is 7. So a plus b has to be 8, and negative a plus 2b has to be 7. So now we have a system of equations. We can use substitution or elimination. Here we're just going to use elimination. So a minus a is 0, b plus 2b is 3b, 8 plus 7 is 15, and so b has to equal 5. And then we can substitute back into either one of these equations the value of b, and we can solve for a. So we see that we do have the original. If a is 3 and b is 5, what we look for is a was over the x plus 2, which is 3, and b was over the x minus 1. We'll go back to the previous slide, and there is a over the x plus 2, and there is b over the x minus 1. So this process works. I will say that there is an alternate way to solve for a and b when you're dealing with two linear factors, and it's not a matter of multiplying a and getting ax minus a and plus bx plus 2b. I stop when I solve these this way, I stop right here. And I realize that when x is 1, this term will have a value of 0. So I substitute x equal 1 all the way through the equation. If x equals 1, then I have 8 plus 7 is 15, and b times 1 plus 2 is 3b. So 3b equals 15 and b equals 5. Then I go back and substitute x equals negative 2 all the way through. So negative 16 plus 7 is negative 9. Negative 3a equals negative 9, so a would equal 3. So I still wind up with 3 and 5. It's just a little more straightforward and a little easier to me than putting it in this form and then doing the systems of equations thing. Now, there is a time where we are going to have to use, we're going to be forced to use this method, and that's why I show it to you here. But for the work that we're going to do here, it's probably going to be just as easy to use this method where we substitute in values of x that's going to force one term to go to 0, and then substitute in the value that's going to force the other term to go to 0. And that gets rid of one of the letters so that you can solve for the other one. So come to class next time and we will practice partial fraction decomposition.